In the last module, we stopped just before we began the derivation for the wall temperature and the bulk temperature variation for flow through a circular pipe subjected to constant wall heat flux condition. So, we start from where we left. This is heat flux is equal to constant case. We take a control volume along the flow direction. As per convention, the flow is taken from left to right. M dot is the mass flow rate, Cp, T bulk mean is the local temperature, bulk mean temperature. When the fluid, the control volume is of a thickness dx, we can use dz also. It would be better to use dz, but most textbooks use dx, so I am also sticking with dx. When you talk of two phase flow situations where there is change of phase across along the flow direction, I would have quality going from 0 to a positive value beyond that location where boiling has started. So, using x for quality makes more sense, but this being a single phase heat transfer part that we are going to study, it does not matter whether we use dx or dz for the flow direction. Mass flow rate outside exiting the control volume is m dot, property same property, temperature has increased Tm plus dTm. This is constant wall heat flux. I am showing only on the top, does not mean that it is not there down or along the circumference. It is a circular pipe. So, heat flux is uniformly given all around. Okay. This is how it is. So, if I do the simple energy balance, E dot in minus E dot out plus E dot generated equal to E dot stored. This is the first equation that you would have seen in the UG heat transfer course. Before we go to the formal derivation, let us list the assumptions that we make here. In any analysis, it is very important to note down the assumptions. It is extremely important to note down the assumptions, and we write them one by one. Steady flow, steady state, that means. So, based on first assumption, this term goes to 0. Constant properties, known constant properties Newtonian fluid, we will use this later. No volumetric heat generation, that means there is nothing, no heat is being generated in the control volume. So, this goes to 0. All the heat that has been supplied goes into the sensible heating of the fluid. So, all Q goes to sensible heating of the fluid. That means no changes in kinetic and potential energy. Other thing, diameter, m dot are all constants. So, it is not a diverging channel or there is no sudden reduction in the mass flow rate, nothing. So, whatever comes in through the circular pipe of constant diameter d, same thing is what is the dimension at the exit plane. So, keeping this in mind, I can write this as m dot Cp Tm, energy coming in. Okay, this is the energy coming in. Energy is also coming in because of heat transfer through the wall. So, heat flux Q double prime perimeter into dz. This is your area. The area of heat transfer is this one, perimeter into dz. Perimeter for a circle is pi into d. If you have a geometry which is like this is side A and B, perimeter is 2 times A plus B. For this rectangular channel, the area of heat transfer will be 2 times A plus B into dx. Here just P into dz, and the energy leaving the control volume is nothing but dTm. So, if I open the brackets, I will cancel m dot Cp Tm, I will get a differential equation Q double prime P dz is equal to m dot Cp dTm, and this is nothing but dTm by dz is equal to Q double prime perimeter divided by m dot Cp. What can we say about this? For a given circular pipe or given geometry, we have assumed this is constant, m dot Cp, perimeter, all are constant. Is that right? Therefore, the right hand side is a constant. What does this mean? dTm by dz or dx, sorry, I am used to writing x, so it's come out as x, come out as z. dTm by dx is constant. What does that mean? The rate of change of bulk mean temperature along the flow direction is constant, or it is a linear variation. dy by dx is constant, represents equation of a straight line, represents that the curve is a straight line. Okay, let us keep that aside and look at something else now. What is q double prime also? H T wall minus T bulk mean. Therefore, T wall local minus T bulk mean local is equal to Q double prime by H. This means T wall local is T bulk mean local plus Q double prime by H. Is it right? Q double prime constant for thermally fully developed flow. For thermally fully developed flow, H is constant, correct? We just showed in the previous module, H is constant. Q double prime is constant because this is constant wall heat flux condition. Therefore, T wall local minus T bulk mean local. That means the difference between the wall and the bulk fluid temperature, or in other words, the driving potential or driving temperature difference responsible for heat transfer, higher, lower. This is your driving temperature difference now. So, driving temperature difference responsible for heat transfer is Q double prime by H is nothing but a constant. What did we show? Tm of x is linearly varying. How did we show that? Because we came up with dTm by dx is equal to constant. Slope of the Tm variation is constant, means it is straight line. If this is varying as a straight line and the difference between T bulk mean and T wall is a constant, that means Tw also varies linearly, same slope. So, delta T is Tw minus Tm local is constant. That means the lines are parallel. Where? Thermally fully developed. This is important. Because H is constant and therefore you get this being constant, the lines are going to be parallel. So, if I draw this temperature as a function of x and let us say this is my thermal fully developed region, linear variation when I derived, I did not have to bother whether it was thermally fully developed or no. So, bulk mean temperature variation is going to be straight line even in the entrance length part. So, this is LT and this is beyond LT, heat flux is equal to constant case. Because H was constant, here we say that this delta T is equal to constant. This green line is variation of wall temperature and the lines are exactly parallel. What happens in the entry region? In the entrance region, what is going to happen is that the heat transfer coefficient is actually going to decrease until it comes to this constant value. So, if I plot the heat transfer coefficient, this is the H. Because this is decreasing like this, the curve for T wall will increase. Why? Because of this relationship. This left hand side is constant heat flux boundary condition. H is dropping, therefore, T wall minus T bulk mean has to increase along the flow direction, which is what is happening. So, this set of curves which shows the variation of the heat transfer coefficient, the bulk mean temperature as a function of x, the wall temperature as a function of x, is something that students must be able to draw, must be able to derive, must be able to appreciate. Thermally fully developed condition, the driving temperature difference remains constant and therefore, we are able to get these two lines as parallel. What did we show? Because this equation is valid, I can also write because dTm, because T wall local minus Tm local is equal to Q double prime by H is equal to constant, dTm by dx would be equal to dTw by dx. Take differential with respect to x, derivative of a constant would be 0, you can take transport derivative to the other side. So, local gradients dTm by dx is equal to dt wall by dx is both equal. Obviously, that is the case because you have got a straight line relationship, and both lines are parallel. So, the slope is the same, the gradient is the same. So, it is not a surprise. So, now let us just go back to our definition of fully developed. D by dx of T wall minus T local divided by T wall minus T bulk mean, and that was equal to 0. This is nothing but 1 over T wall minus T bulk mean. This can be written as dt wall by dx minus dt by dx, correct. So, this can be written this way, this is equal to 0 implies dt by dx is equal to dt wall by dx. Is that right? In the previous module, when we said thermally fully developed, we took the derivative with respect to r and said it was not a function of x. Now, we are taking the derivative of this theta with respect to x and we are saying this quantity partial derivative will be replaced by regular derivative because T wall is only a function of x alone. Okay. So, what does this bring me to? dt by dx local temperature variation in the x direction. What is x direction? Bulk flow direction, axial direction. This is equal to dTw by dx, very good. But then we also showed this dTw by dx is equal to dTm by dx. So, this is dTm by dx, and what is the value of this quantity? dTm by dx we showed is a constant given by q double prime p divided by m dot Cp, q wall perimeter by m dot Cp, which is a constant. So, a very useful and important relationship has been obtained as to how wall temperature, bulk mean temperature and the local temperature with respect to the flow direction varies, this is all equal and is a constant value. And this gives us the fact that gradient, what is heat transfer coefficient? dt by d, we showed there, dt by dr at r equal to capital R, which is representative of the heat transfer coefficient, that is constant. That means heat transfer coefficient was not varying in the flow direction after the thermally fully developed length started. This is now giving us an additional important thing, dt by dx. Go back to your hydrodynamics. Hydrodynamically fully developed, what did we say? Du by dx is equal to 0. Now I am saying dt by dx is not 0, but it is constant. I hope you will be able to appreciate the difference here. So, something special happens because of fully developed. What is that special condition? Du by dx equal to 0 hydrodynamically. Thermally, dt by dx is equal to dt wall by dx is equal to dt m by dx, regular derivatives, which is equal to a constant, which is nothing but heat flux times the perimeter divided by m dot Cp. This result, temperature gradient, is independent of x, thus the shape of the profile does not change. dt by dx, the shape of the profile does not change as I move along the flow direction. That is an important conclusion that can be drawn from this relationship. So, dt by dx is equal to dtw by dx is equal to dtm by dx. For a circular pipe, perimeter is 2 pi r, m dot is equal to rho into u bulk mean into pi r squared. So, if I write this, dt by dx is equal to dtw by dx is equal to dtm by dx is equal to q double prime. I am just substituting here 2 pi r divided by rho um bar pi capital R squared Cp, pi r cancels, pi r cancels. So, this is nothing but q double prime into 2 divided by rho um bar r Cp, which is also a constant. Okay, which is also a constant. Okay, next we go to constant wall temperature case. This requires a little bit explanation as opposed to constant wall temperature case because of the inherent complexity that we get because of this Tw equal to constant. Constant heat flux case, what was my temperature profile? The temperature profile came out so nicely. Constant wall temperature case, it is achieved by having a phase change on the outside. So, if I have a tube and you want it to be subjected to constant wall temperature, so the T wall has to be constant. So, this is which process occurs at constant temperature? Phase change process. So, I should have evaporation or condensation occurring inside the tube such that the wall temperature is constant, because the inside bulk temperature of the fluid is constant, and then the heat exchange can occur between the fluid from here to here, which is subjected to a constant wall temperature case. So, drawing the diagram for T as a function of x is very straightforward here. Let us say this is T wall is equal to constant, not a function of x. So, I can have two situations where the fluid is getting heated or the fluid is getting cooled. The analysis for both these cases is going to be identical. How is it? How do we say that? Well, if I say the fluid is getting heated, and there is significance to this arrows that you can tell the students, we will understand this in heat exchanger. So, the arrow one is going from left to right, other is going from right to left. So, the bulk fluid temperature is supposed to vary like this. So, what I am trying to say here is this is the local driving temperature difference. Okay. So, T wall local minus T bulk mean local is the driving local temperature difference necessary for heat transfer to occur. Okay. What is this? This is constant. If T wall is greater than T bulk mean implies heating of fluid. If T wall less than T bulk mean implies cooling of fluid. Whatever be the direction of heat transfer, what can be understood from this diagram? That the driving temperature difference progressively decreases along the flow direction. So, delta T, T wall minus T bulk mean is decreases as the bulk Tm increases, correct. So, as x increases, T bulk mean increases, T wall equal to constant, T wall minus T bulk mean decreases. I hope everybody is able to appreciate this. What does this tell me? Heat transfer rate Q or Q double prime, which is directly related to T wall minus T bulk mean, decreases as x increases. So, having a constant wall temperature case implies heat flux. So, Q double prime varies. What was it here? Heat flux was constant. Therefore, the wall temperature and the bulk fluid temperature was varying. It so happened that these two were varying at the same rate, but the point being, here I was able to keep heat flux constant and therefore TW and T bulk mean was increasing. Here I am keeping T wall constant, therefore TW is constant, Q double prime and T bulk mean vary. I choose what I want as a constant, I cannot control the other two. Q double prime is constant, then I have to allow T wall and T bulk mean to vary. I hope this can be really brought out to students effectively. Okay, what is the implication of this? Well, unlike my case where I could get a very nice relationship of this kind, okay, here if this is a pipe, let me say this is a pipe, fluid is flowing through a pipe here, and the fluid at inlet was at temperature Tm inlet, Tm local and Tm exit is the exit temperature. Inlet bulk mean temperature, local bulk mean temperature, exit bulk mean temperature. Flow is going this way. So, x is equal to 0, x is equal to L. Okay. So, if I were to plot the temperature profiles, T wall and this is my T m subscript E, this temperature, this is x is equal to 0, x equal to L, this is my T m subscript E, this is my T m subscript I. The inlet temperature difference delta T inlet is T w minus T bulk mean inlet delta T I. The exit temperature difference delta T E is T w minus T bulk mean at exit. What can we say about these two? Delta T I is greater than delta T E. Very simple. That means Q at inlet, that instant, is greater than Q at outlet, the exit. The heat transfer in a small region near the inlet is going to be much greater than what it is at the outlet. Who dictates the slope of the curve? Energy balance. So, m dot into Cp into T local delta T is equal to Q double prime. This is going to dictate the nature of this curve, whether it is going to go this way or whether it is going to go this way. All I am trying to say is, smaller mass flow rate, the temperature rise would be higher. Larger the mass flow rate of the colder fluid, temperature rise would be smaller. So, the nature of the curve, the shape, etc., would be identical. The slope of the curve would change because of the mass flow rate. So, Q at every location is not a constant, it is varying. So, what do I do? What is the temperature difference that I take to do the analysis? Should I take T bulk mean at inlet or T bulk mean at the outlet, or should I take average temperature, that is T bulk mean at inlet plus T bulk mean? So, T local representative is Tmi plus Tme by 2. Is this acceptable? What do I take? So, this makes us come to a concept of arithmetic temperature difference. So, arithmetic temperature difference is nothing but delta T inlet plus delta T exit by 2, that is T wall minus Ti, I am dropping the subscript m, plus T wall minus T bulk mean exit divided by 2, which is nothing but T wall minus T bulk mean inlet plus T bulk mean exit by 2, delta T arithmetic mean, arithmetic. So, this was thought as one of the representative temperature differences. Well, the biggest problem with this is that you are assuming this temperature to vary linearly. Bulk mean temperature is varying linearly. When I take average, I am assuming that dt m by dx is constant. Then average makes sense. If the slope of the bulk mean temperature is changing along the flow direction, how can I take the temperature variation to be continuously, to be a constant? Because it is varying, because dTm by dx is not equal to constant, this definition of delta T arithmetic mean is not very useful. So, in the next module, we will develop the concept of log mean temperature difference, which is directly useful in the heat exchanger application, and then derive expressions for the temperature variation of the bulk fluid based on this log mean temperature difference and the local heat transfer rate. We will also introduce the concept of overall heat transfer coefficient. Overall heat transfer coefficient. Thank you.